In the first couple of chapters, we learned some techniques to describe data, such as organizing data into frequency distributions, showing them in the graph of a histogram and a pie chart, and measuring the center of the data with the mean, median, mode, and measuring the dispersion of the data with the standard deviation. And then we lay the foundation for inferring or predicting the data with the study of a probability and a probability distribution. Okay, try to recall that probability distribution cover all possible outcomes of an experiment and the probabilities associated with each outcome. We use it to evaluate the likelihood of something occurs in the future. So when we predict the data, we usually determine something about population which based only on the sample. Okay, here let's try to recall how we define the population and the sample. Okay, the population is the entire group of the objects under consideration, and the sample is a part of that population. It's hard sometimes to get to know the data of the population. It's very expensive or time consuming. And if we select the sample properly and analyze them correctly, the sample information can be used to make accurate assessment of the entire population. We can use all the knowledge we learned, all the techniques we learned to study the sample to predict the features or characteristics of the population. Again, let's grab some concepts first. Parameters. Parameters are the values that describe some characteristic of a population, such as mean or median, right? So population mean is a parameter of a population. Statistics are the values calculated from a sample, such as the sample mean, x bar, right? We use x bar to represent sample mean. So x bar is a sample statistics. Okay, once again, values calculated using population data are called parameters, and values computed from sample data are called statistics. Next concept is sampling error. Okay, so sample statistics will vary from sample to sample, right? It's easy to understand because samples are different, right? Parts of the population. So sampling error is defined as the difference between the sample statistic and the population parameter, such as the difference between the population mean and the sample mean, population standard deviation, and sample standard deviation. Here you go. This is the formula for the sampling error of the sample mean, right? So sampling error of the sample mean is the difference between the sample mean and the population mean. So it's x bar minus mu. A larger sample size will provide a smaller average sampling error. And the non-sampling errors means the errors has nothing to do with the sample, okay, with samplings. So it's just the result of other issues, such as ambiguous survey questions or the questions that lead respondent to a certain correct answer, or data collection errors. So they are not related to sampling variability. Why should we know about this? Because we want to be clear about how accurate the result we get from the sample can be used to represent or verify the population. Here is the very, very, very important theorem. Okay, this theorem showing us why we use a sample, right, to prove or to know about the population. It's a central limit theorem. This theorem states that the sample means of a large size samples will be normally distributed regardless of the shape of their population distributions. So this theorem built up the connections between the sample population and the normal probability distributions we learned. Just want you to know that this is a key concept. We're going to use it repeatedly throughout the rest of this class. Okay, now let's check this example to show you what central limit theorem is. Assume there is a population. Okay, the data gonna be the age from all of the 4 people. So the population size is n equal to 4. And the random variable x is the age of individuals. So values of x gonna be 18, 20, 22, 24 of those 4 people. We calculated their population mean. Okay, mu is we sum up all the 4 people's age and divided by 4 is 21. So the average of their age is 21. 21 is population mean, and sigma is 2.236. Okay, now let's assume we're gonna take samples out of that population. So the sample size is gonna be the 2, means we randomly take the sample of 2, right? So we take the 18 and 18, means the 2 numbers out of that 4, or 18 and 20, or 18 and 22, or 18 and 24, or the 20 and 18, 20, 20, 20, 22. So that means we list all the possible samples. There are 16 possible samples, right? 16 pairs of the samples, and then we calculate the sample mean for each possible sample. The mean of this group of sample is 18. The mean of this group of the sample is 19. The mean of this group of sample is 20, and so on. We got all the sample means. And we have 2 discoveries. One is if we list the probability distribution of those sample mean, we found out they distributed normally. Okay, the probability distribution of the sample mean is normal probability distribution here. Second, we found out the mean of the sample mean, right? We sum up all the sample mean. We found out the result is 21, exactly same as the population mean, and with a smaller standard deviation. Okay, so according to the central limit theorem, sample means from a sample of a sufficient size drawn from any population will be normally distributed. In most cases, sample size of 30 or larger will result in sample means being normally distributed regardless of the shape of the population distribution. If the population follow a normal probability distribution, the sample mean will also be normally distributed regardless the size of the samples. And for any population, the average value of all possible sample means computed from all possible random samples of a given size from population is equal to the population mean. Okay. The standard deviation of the sample means computed from all random samples of size n is equal to the population standard deviation divided by the square root of the sample size. So we call this standard error of the mean. Okay, now let's try how we use this central limit theorem to help us get to know the population from the sample. For example, suppose people drive an average of 12,000 miles per year with a standard deviation of 2,580 miles per year. Question: what is the probability that a randomly selected driver will drive more than 12,500 miles? Well, we cannot answer this question without more information about the population probability distribution, right? However, if we put this way, what is the probability that a randomly selected sample of 36 drivers will drive on average more than 12,500 miles? Because of the sample size is large enough, greater than 30, we can use the central limit theorem to answer this, because the sample, the sampling distribution of sample mean gonna tend to the normal probability distribution, and we can use the knowledge we learned from normal probability distribution to find out the probabilities that the value follow into the certain range, right? In this case, the value falling into the range of x bar greater than 12,500. Okay, since n is 36, we can apply the central limit theorem, so x bar will be normally distributed with mean and a standard deviation. Okay, here the mean is 12,000 and the sigma is the population standard deviation over square root of n, right? That is the standard error of the mean. That's also the mean, the standard deviation of the sample, equal to the 2,580 over square root of 36. We get 430. Remember last time we introduced how we carry out this process, right? That is, next we find out the z-score for the mean. So the z-score gonna be the x bar minus the population mean and over the standard deviation of the sample, right? Standard deviation of our sample we just calculated. Let's continue. So the z-score equal to x bar minus mu sub x bar over sigma of the x bar, that is 12,500, right? Is this value, and minus the mean, the population mean, and divided by the standard deviation of the sample, that 430, equal to 1.16. Once you know the z-score of the 1.16, then we're gonna use the z-table to find out the probabilities. In the z-table, the probability of the x, of the 1.16, the z-score is 1.16, is this part is 0.8770. So the probability that x bar greater than this point gonna be this area, that is 1 minus 0.8770 is 0.123. So which means there is a 12.3% probability that the randomly selected sample of the 36 drivers will drive on average more than 12,500 miles. Okay, please let me know if you have any questions. And again, the email is always the best way to find me.